one. Now we're in chapter 4. We've been talking about derivatives, and we looked at in 4.1 and 4.2, we looked at the closed interval method, which the closed interval method is a way of finding the absolute max and the absolute min of a continuous function on a closed interval. So what we learned in there was that you could always find an absolute max and an absolute min, and that sometimes it might occur at an endpoint, or sometimes it might occur at a local max or a local min, but that you could always find it if it's a continuous function. We learned a term in that section called critical values, which is where the derivative of a function equals 0 or it's undefined. So we will also hear that term. We'll be using that today when we look at these. So how derivatives affect the shape of the graph is what we're going to be looking at. So to get us started, again, you have a worksheet to follow along with. I want us to consider a graph. So I'm just going to draw a picture of a continuous function just so that we can talk about something. So if I've got something that sort of looks like this, and I want to label these points here, let's say maybe let's label this point, and let's label this point, and these endpoints. I'm going to call this one maybe 2, 1, and I'm going to call this one maybe 4, 4, and I'm going to call this one 6, 3, and I'm going to call this one 10, 6. Okay, so let's just look at this. This is something you learned to do a long time ago, but I just want to say, where is this function increasing and where is this function decreasing? We know how to do this. We've known how to do this a long time. So it's increasing basically where the function's going up, and it's decreasing where it's going down. So let's see. It's increasing from 2 to 4, and you can do a U. You could also just do a comma. It's okay. It's also increasing from x is 6 to x is 10. So we know when we're talking about where does something increase and where does something decrease, we always write down the x values. Where is this guy decreasing? He's going down from 4 to 6. Okay, so let's just make some observations about this. We also have looked at functions and how we might map their derivatives or get a graph of their derivatives. And we know that we would do that by considering the tangent, right? The tangent line. So if we look at the tangent here, the tangent line, it's positive, and the tangent line here is negative. So that means the derivative would be positive here and it would be negative here. And again, it would be positive here. So we can make some observations. We'll notice that when the derivative of x is positive, then f itself is increasing. And when the derivative of x is negative, then f itself is decreasing. So we see that by having some knowledge about where the first derivative is positive or negative, then we know what's happening with the graph of f itself. So let's just look at this first example here. It says find where f of x is 3x to the 4th minus 4x cubed minus 12x squared plus 5. Where is this fella increasing and where is he decreasing? So we're going to say we don't have a graphing calculator. If we were face-to-face in the classroom, we would have proctored tests, and you would not have a calculator for any of this. And so I will test you in a manner so that you will have to know how to do this without just throwing it in a calculator. So let's see, how would we find out where this is increasing or decreasing? We could take the derivative and say, well, where is this derivative, positive or negative? So let's find the derivative. F prime of x is equal to 12x to the 3rd minus 12x squared minus 24x plus 0. This is the derivative. Now, if we can figure out where this guy is positive and negative, then we can tell where this function is increasing or decreasing. I'm going to show you 2 ways to do this. You can choose to do it however you want to. Sometimes it's easier to do it one way, sometimes it's easier to do it another way. What I'm going to first choose to do is graph this, okay? So I'm going to graph this function how will I graph it is I'll try to find the zeros. So let's see. Let's try to find the x-intercepts or the zeros. I could factor out an 12x, leaving me with x squared minus x minus 2. If I set this equal to 0 and solve, this will give me the x-intercepts. Let's say 12x cubed minus 12x squared minus 24x, okay. 12x, x minus 2, x plus 1, is this right? X squared. Yep, okay. So what I can say is, oh, I see zeros here. So this is a little polynomial, and this is super easy to graph. So if this is what springs into your mind, you could get away with it this way. So I'm going to show you two ways. This is one way you could do it. You go, okay, what are my x-intercepts? X is 0, x is 2, x is negative 1. What are their multiplicities? 1, 1, 1, which means it's going to cross, cross, cross. What is the end behavior? Well, this is the third power, odd. Positive, odd means, positive means it's going to be up to the right, odd means it's not going to follow the right direction. You could do a quick sketch of f prime, all right? Here is the 0, negative 1. Here is the 0 at 0, and here is 2. All right, we know it starts down, and that it's going to cross, 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 and this is negative 1, and this is 0, and this is 2, and you could say, where is this guy positive? Well, he's positive here and here. And he's negative here and here. So you could say f is increasing where it's positive from negative 1 to 0 and from 2 to infinity. And f is decreasing from negative infinity to negative 1 and from 0 to 2. We could figure it out that way. I'm going to show you another way to do it, which you could also do it this way. The second way is you could find the critical values, which is where f prime of x equals to 0 or is undefined. So these are also known as the critical numbers or the critical values. Once you find these, instead of graphing it, sometimes it's super easy to graph it, but what if it's not? Then, or you don't want to do it that way, here is an alternative. You can draw a number line. Here is a number line. And you can mark the critical values on there. So here is negative 1, negative 1. Here is 0, 0. Here is x is 2, all right? And what that does is it splits up your number line into different regions. Then you can do something called test points. You can pick a point that falls in this region of the x-axis. So something to the left of negative 1 maybe would be a negative 2. Something in between 0 and negative 1 would be maybe negative 1/2. Something between 0 and 2 would be 1, and something bigger than 2 would be maybe 5. These are just simply representative points for these regions. So, what do you do with this? This down here, these are numbers that I plug into f prime. So here's f prime. And I'm going to say, well, what I'm interested in is not really the value, but whether that value is positive or negative at this point. So I plug in negative 2 here. 12 times negative 2 would give me a negative. All right. Negative 2 minus 2 gives me another negative. And negative 2 plus 1 gives me another negative. So I see that if I'm multiplying a negative times a negative times a negative, this will be a negative. That's what I was interested in. I have a bad habit of using this point after I've figured out what I needed it for, so I mark it out. That means if f prime is negative, then the function itself is decreasing. This is what's happening with the function f itself. Maybe I'll make that a different color. With f itself, the function is decreasing right here. That's what that means. Okay, so when we get to negative 1/2, what we would do is we plug it in here. So 12 times negative 1/2 is a negative. Negative 1/2 minus 2 is another negative. Negative 1/2 plus 1 would be a positive. So we have a negative times negative, which is a positive, times a positive, which would make this positive. Okay, I'm going to try to do better with my colors and stay consistent. That's positive. That means the function f itself is increasing during this region. We could plug in 1, and when we do that, we'll find that 12 times 1 is a positive. 1 minus 2 is a negative. 1 plus 1 is a positive. Positive, positive, negative gives us a negative. That means the function itself is decreasing during that time. How about 5? 12 times 5 is positive. 5 minus 2, positive. 5 plus 1, positive. This is a positive. This is increasing right here. All right, so what did we discover? We discovered that from, remember this is -1 and this is 0 and this is 2, that when f from negative infinity to -1, the function is decreasing, like this. And from 0 to 2, the function is decreasing, like this. And from -1 to 1, the function is increasing. And from 2 to infinity, the function is increasing. So, those are alternate ways. This, sometimes it took longer in this instance. However, sometimes you don't have a polynomial that's easy to graph. So this is a good method to make sure you can do. Now, we can learn some more information from this, because we have, just below this, we have something called the first derivative test. So it says this: suppose c is a critical number of a continuous function, like this. These were critical numbers. If f prime changes from positive to negative at c, then f has a local maximum. If f prime changes from negative to positive at c, then there's a local minimum. If it doesn't change, like positive, positive, or negative, negative at some critical value, then there's not a local max or local min. So problem number 2 says, find where this same function, find where this function has a relative max or a relative min. So what we would do is we would find the critical value. We take the derivative. We would find the critical values. Here they are. Then we would look and say, hey, did it change from negative to positive, from positive to negative, from negative to positive? Or here, it's easy to see. Here it went from negative to positive. Uh-oh, this is a local min. This is a local min right here. Local min. Did it go from positive to negative? Oh, yeah, it did. This is a local max. Did it go negative, positive? Yes, this is a local min. So, that we've identified the local mins. If we need to know the value, you plug these x values into the original function. So we can say, okay, this is number 2. We've identified that there is a local min at x is -1, and we plug that into the original function. So if we plug in -1 here, we get 0. And then if there's a local max, it went up and down. Here's the other local min. Let's do both the mins. The other local min is here at 2. At 2, and a -27 is what you get when you plug that in. And then there's a local max. Local max at x is 0. And you plug that in and you get 5. So here's the deal. You got to be a little careful. What the first derivative told us was where the original function was negative and positive and negative, decreasing and increasing. And if there's a change at a critical value from negative to increase or vice versa, you have found a local max or local min. So that's what we discovered using the first derivative test. Now, there's more to come. We can talk about the second derivative test, but before we do that, we have to talk about concavity. So, I'm going to take a short break just so that you guys can have a break, and we'll pick up with concavity next.